Okay, well, for people who are joining this live stream, this is a meeting talking about NBody simulation in Wolfram language, aimed at a future version of Wolfram language. This is second or third meeting we've had discussing this topic. So let's see. We actually have some runnable code here. Let's hope this actually can load in. Okay. So, oh, look at that. All right. So Rob, is this production grade code or is this still just demo stuff?
This is not production grade code at this point. It's getting closer. That's pretty much the interface we talked about though.
Okay. All right. So what this did, data not a notebook store now. How big is it? Okay. Does that work if I say store now? Seems to.
You should be able to reload that.
Okay. All right. So if I copy paste this, I mean, at least copy paste, that will have the complete thing inside it. Who knows? Okay. What's an example of something I can query for this?
Position.
Magnificent. Okay. So there. That's very nice. So then for that gives the positions of those two bodies. So if I say, let's just see whether this works. If I just say, yeah, that is insane. That is insane.
Well, that's what's necessary now to get the different colors to work.
Okay. Well, that should be a discussion. I think we have a discussion later today about missing values in visualizations.
Mm-hmm.
Actually, if people, we could live stream that one.
It's evaluation versus non-evaluation.
I know this one is evaluation versus non-evaluation, which arguably, particularly with a compiler, we could be more sophisticated about. And that's probably worth mentioning to Tom. Or is it crazy? Is it far out of reach?
No, I don't think so. It's just the opposite. Because like without having it there, you don't know what it will be. That's why you need to evaluate.
Okay, but the through of values of whatever is pretty crazy.
Well, see, that's because the position thing returns the interpolating function, so you have to get the arguments to those in some nice way.
I realize that. But I mean, I think this particular thing, if we say %for, I mean, if we were to say, just to try to understand the idiom, if we said this /at, B1, B2, humpty hump, then we get those, and we still don't have functions, do we? The thing is that in terms of this, right, if you wanted to say position of T, if you could insert the T in here, then you would be in much better shape.
Well, right. And if you look farther down, I think that's some of the interface we discussed. And I have a bunch of examples of different ways you can get.
Okay, fine. All right. So we're going
to some of these things. And I think basically being able to do plots and stuff will give us some more ideas on that from what I just did too.
Fine. What's this method flatten functions? True?
That's supposed to make it so that I could do it without the evaluate. So I just left them in for now. So it doesn't evaluate, but it doesn't work right now anyway. So it's sort of trying to ignore that.
Wow, this is really cool. So this is symplectic integrated. So the total energy remains fairly constant.
No, this is just the default integrator. For the symplectic one, it's going to take some more work, but it is going to be possible to use it in some sense.
What does in some sense mean?
Well, the problem is the symplectic. So the symplectic integrator, for it to be symplectic and conserve the energy, it needs to have constant steps.
Okay.
So right.
There aren't adaptive symplectic integrators?
Not that I'm aware of. When I asked Mark, he didn't know anything that we had that that does that. So one thing we could do is we can, with what we have now, we could basically monitor the energy, and when that seems to be locally changing, we could sort of stop and then restart with a different step size, and we can lose a little bit of energy that way. But I think that the total loss would be pretty minor. But again, that involves another level of development than
fine,
what we're
fine.
doing.
Well,
here.
let's not worry about that right now. I thought the symplectic integrator. I mean, if we can have a method where you say use the symplectic integrator, if energy is what you care about, as opposed to fine detail of the trajectory, then you might want to choose that.
Right.
They're of course related.
What are related?
Like if the energy is not conserved, very probably your trajectory is also wrong.
I understand, but you have no hope if the adaptive steps are wrong and you've got this little thing that's zooming around a black hole. It's just going to be completely wrong. Even though it may conserve energy, the trajectory will also be, I mean, even though the symplectic integrator is forced to conserve energy, the trajectory will be completely wrong unless it's adapted for that, high curvature thing around the black hole or whatever, if I'm not mistaken.
I'm not convinced, because the symplectic one does not just preserve energy, it also preserves some higher level invariance.
Right. Well, what yeah, I think we can actually, monitor some conserved quantities in this, I just did this experimentally before. We can monitor some of the conserved quantities with the symplectic one. And then when that seems to be locally changing, that gives us an indication that our step is too large. And then we could go back. We'd have to sort of back up and say, okay, we'll use a smaller step for this section.
But Michael, I mean, what other constants of the motion are not trivially conserved? Is center of mass? No, center of mass might not be conserved either, because we haven't reduced the coordinates or anything. Is that correct? But what else? What other constants of the motion are there that we can monitor? And do we know
angular momentum?
Fine, and your claim is that is not structurally conserved. That would have to be conserved by virtue of the actual integration.
I'm not sure what this means.
Well, I mean, there are some things like if we had reduced coordinates and we had reduced out the center of mass, then it is not an interesting statement that the center of mass is conserved.
Right, because it's no longer there.
Right. So you claim that anything that is still there, any combination. So in particular, we could imagine an option that says monitor these quantities, for example.
Yes.
Yes.
And of course, you would have to know that they are preserved if you want to, because most of them will change.
Well, I understand, but there, for the inverse square law, there are definite ones that are conserved, right? For every one of that first argument.
Yes.
I mean, I don't know what other ones we have here, but what other named ones do we have? Do we have other named ones?
Well, the only other named one I've really tested is gravitation, which is the same thing.
Okay. What about Van der Waals or something? I mean, or Leonard Jones or whatever. I mean, are we imagining that we'll have a Leonard Jones, a thing called Leonard Jones, and does that even make any sense?
I think it would totally make sense.
Okay. But I mean, is there an obvious Leonard Jones of r to the 6 minus r to the 12 or whatever thing? Or are there like...
Modulo the values of the factors of the powers.
Okay. But then, I mean, people go around, being very proud of their atomic potentials and things. And we could imagine curating a collection of some interesting atomic potentials, yes?
Maybe.
I mean, I know we have some users who specifically study atomic potentials. We could probably ask them for these. But if we had those, are they useful, or are they? I mean, people do semi-classical computations, don't they? I mean, they're not solving Schrodinger equations for those things. Isn't that correct?
I think in more cases they use some version of Schrodinger equations.
Okay. All right. So then maybe that's not so useful. But okay. But in any case, for the inverse square case, I mean, are there any other potentials? Are like harmonic potentials of interest?
Definitely.
So we should have that as a named thing, right?
Yeah. No, I have a bunch of named things. which we had in the first version.
Okay, fine.
So
the problem with the harmonic potential is that, which guys are connected by which springs needs to be specified, doesn't it? And I don't think we have an obvious way to do that. Like inverse square, you don't get to shield gravity. Am I making sense?
Yep.
But in the case of springs, some things are connected and some are not. So, as I say, did we address that or not?
No, we did not address that.
Okay. Well, we should address that. I mean, I think that would be some kind of thing where we say harmonic arrow, and then we give some sparse array, which gives the spring constants. Does that make sense? You guys seem to be very silent. Rob?
Well, yeah, that's going to be a matrix.
I mean,
a matrix of bodies, which indicates the spring constant between.
It definitely makes sense, but in this
body.
moment, it kind of loses a little bit the NBody flavor. It becomes a degenerate case of NBody.
You're right. I mean, are we committed? Well, I don't know. I mean, the Fermi-Pastor-Coulomb problem and things was that was intended to be an NBody-like thing.
Well, maybe. I mean, it's an interesting idea you bring up. Maybe there should be a way of specifying, that a potential function, some constant for that is specified by a matrix or something. And that could be the interaction constant between.
Well, I thought we talked about that.
No, we did not talk about that.
Okay, because it can take in the mass, the position, etc., even the velocity. It can be a velocity-dependent potential potentially.
Yes.
So this thing here can be a function, and the function is simply fed. The association for each body, correct?
Right, but that assumes that each body interacts with each other body via that function based on the properties.
Function just end up being zero. That's what a sparse array would do.
Right, that would be a way of telling that function that it's zero for those two bodies.
I understand, but the other thing we could do is just return. Look, in the function, we could have a sparse array. See what I'm saying? Right? In the actual function, in the potential function, the value would be something which indexes into a sparse array. Make sense?
Sort of, but it's hard to see what the actual definition would be.
All right, okay. Let's come to that. Let's go down the rest of this, but please don't forget that, okay? Okay. All right. Data on the body B, yes, we know. Data at t equals 1. Okay, that's pretty reasonable. Okay, so wait a minute, what is this?
That's all the data at t equals 1.2.
So that's a bit of an elision. So then you're saying if there's a non-string argument, you're taking it as a time value.
Yes.
And if I just wanted position here, I would say B1, 1, and then position. Is that right?
I think it'd be B1, comma, position, comma, 1. I don't remember the order.
Well, I think it would be good if it could be B1, position 1. What is that background noise?
Sorry, that was my chair creaking.
Okay. There. Okay, so you say, if I say this, you think you're going to get, oh, beautiful.
Yeah, and then if you do of 1, either curried or otherwise of 1, I think it'll give you the position at that time.
Magnificent.
Yeah. Well, this was your idea, Stephen. So.
Oh, well, then it's less magnificent. Okay.
Right.
Oh,
still
well.
magnificent, but
okay, fine. Okay. Wouldn't it make sense? Shouldn't we say? Does it make sense to say position equations? It just says equations. That's okay, I think. No, Hamiltonian equations. Okay. And where did these formal variables? These are just Q dot formal Qs.
Formal Q subscripted with the body name.
How is the subscripting done? Just with subscript?
Just with subscript. Nothing fancy. I may use indexed. I can't remember. Either subscript. No, I think it's just subscript because these are not.
But so could I feed these into, I mean, like this is a two-body problem, right? So if I take that, I should be able to feed that into DSolve and it should be able to solve it, shouldn't it?
No chance.
I don't think it's, well, DSolve doesn't, one thing is DSolve doesn't know dot.
What there's no dot?
But this doesn't matter. It's still a derivative. It's just a variable.
What do you mean?
Far too non-linear for DSolve. Coupled non-linear, you have not much hope.
But I mean, Newton managed to solve this.
By hand.
It was a long time ago.
If you wrote it in the right form, DSolve might have a chance, but with a see, I kept the dot in there because
what dot? What are we talking about? Dots? Those aren't dots. Those are just formal variables.
No. The dot on the center of the denominator.
Oh, I see.
That's our.
Yeah, that will make it hopeless for DSolve, right?
Our dot product, exactly, because that works more efficiently numerically than using. It's tidier for our numerics than using norm is.
Although norm should definitely work efficiently too.
Yes, norm would work.
But I see. So your claim is that if you put it in coordinates, it might be able to do it, but it has no hope in this form. Is that a true statement, right, Michael?
I think there's no hope because what Newton did was not getting Q of t. He got R of phi, which is double implicit with respect to Q of t.
Oh, I see. What is the formula for Q of t? It's something involving elliptic functions, or what is it?
I'm sure it involves elliptic integrals.
Okay. So with a change of variables into action angle variables or something,
then the situation looks better.
Right. Mm-hmm. Okay. It would be a good test case for DSolve. It might be worth pointing that one out to Roger. I mean, he may just say it's hopeless, but okay, three-body problem. Here we come. Okay. So I still don't understand why you need this big mess here, given that you've got these quite clean ways to get, I mean, given that you can just say, if I do data here, it's very zippy, I have to say. Okay, so now if I say data of, and what you're telling me is I need to say the body name, like, what am I saying here? 1 or something, is that right? It's kind of an awkward body name, isn't it? Because it's going to conflict with other things. If I say data of 1, how does it know what to do? Well, it decided it was a body name. If I'd said, okay, fair enough.
Well, that's because I chose. See, I used 1, 2, and 3 as the names in this case.
No, I realize that. But if it was 1 point, I shouldn't. Presumably, I can't use 1 point as a body name.
Right, because then it'll get confused. I think it chooses the body name before the time, but that's potentially ambiguous.
So let's say 1, 2, 3. Will it work? Is it listable over those?
Don't think I made it listable.
Okay, so if you did make it listable, that very nice thing would presumably give you, let's see if it works with just a 1 there. No, that didn't work. So, but that should work. Maybe the curried form will work.
Right. I think the curried form might work.
Okay. That's fine. Okay, so now let's take a look at the 1, 2, 3, 2 position. It didn't work.
Try an all instead of 1, 2, 3, because that I may have overloaded that.
Okay, but you should make 1, 2, 3 overload.
No.
Sploth. Okay, so that should work as well.
Okay, so yes, that's a good idea to list over. Use.
Right, because then that's a pretty clean thing. Data all position of T. That's a pretty clean way to get this out. And then what that would return is hopefully something that parametric plot could, it would return a bunch of interpolating functions of T, and then parametric plot will hopefully do its thing and color everything happily.
Well, right. That's why that flatten functions is there, so that if I don't evaluate, it would still work and color things. Without that, it's not going. It's going to color everything the same.
Why?
Because that's the way it works.
But it shouldn't. Why does it do that? I mean, if you've got, look, if you've got plot,
because it decides the color beforehand. It doesn't at every evaluation count, because some might be complex. How many good values do I get? How many colors do I need? So sometimes 2, sometimes 12.
No, but I understand. But if it structurally has an association like this, why can't it figure it out? I mean, it does figure it out. Look, listen, you're going to feed it in. Apart from the evaluate, I don't think it needs anything else. I think the evaluate will be sufficient.
Yeah, that's what I'm pointing out, is you have to have the evaluator. It doesn't.
That's fine, but then you don't need this weird method option.
Mm-hmm.
Okay, fine. Okay, so that's quite magnificent. And, oh, I see. These are 3-body problems in 2 dimensions.
Yes.
What the heck is that? Oh, I see. That's very beautiful. Wow.
Yeah, I kind of like that too.
So.
Okay, and this is showing you can restart. You take the data and you can restart it and continue further.
It's pretty funky that you've got a 6 there, which, if you had a 6-body problem, your 6, you get what I'm saying? It's going to get confused. Oh, no, it isn't.
But that's just an example of where the time it's integrating to. So if I'd use 6.28, right. That would have been less.
I understand that. I'm just saying that there's an ambiguity, because if you take that particular thing is doing, I get it. In that case, it's not ambiguous.
Mm-hmm.
Okay. MultiBody in 3D. Why are you doing, random points on a sphere?
Mm-hmm. That's just a starting condition.
What is the default here? Oh, I see. 24 megabytes shouldn't be default in the notebook. Wow. These energy things are very good. It's surprising. Okay.
Well, if you looked at just the energy, you might not be quite so happy.
I was just going to say, look at it kind of like it's a gigantic scale. The fact that it's straight doesn't say much.
Okay. Well, it says that it's not getting round off between those things. Okay, let's look at the Earth, Moon, Sun.
So I just chose, I sort of pecked around our entity stuff to find initial conditions.
That's really cool.
And one thing I'll mention, and I think this is so I think, with the right person working on, functions and stuff, I integrated this with the entity stuff. So notice I didn't have to specify the mass. It just automatically goes and tries to find it if it's not already given.
Hold on. Where is it finding the mass? So you're saying
it's using the so these things, these bodies are entities themselves.
Right. Well, that's clever of you.
When it's an entity, it goes and tries to find the properties it needs automatically.
Yeah, that's cool. That's really cool. Okay.
And the difference between gravity and inverse square is that gravity actually uses the gravitational constant and units.
That's very nice. Wow. Okay. So that's the orbit of the moon. Yeah.
That's the bottom one is the orbit of the moon around the Earth.
Because this thing here is the moon versus Earth. Is that correct?
Right.
That's great. What does that actually look like? Okay. So that's a bunch of lunar months.
Now, and I haven't checked that for accuracy or whatever, but
well, see if you can get the eclipse. We did look at that if you look at the blog post I wrote about the eclipse, I guess Jose helped with that, or who helped with that? We did a bunch of these integrations.
Yeah, Jeff and Jose.
And me. Yeah.
Yeah, it was Jose.
Like Jose provided the initial conditions, and then for a couple of days we can explicitly solve equations of motion and get it reasonable.
Right, and this should be able to reproduce those results. This code.
Right. That's more or less the code I used.
Fine. And I mean, all these helio coordinates, I know we're working on slowly the whole astro coordinate system business. I don't even know. I have no idea where the zero, is that the first point of Ariès or something is the zero? I don't even know what these coordinates really are.
It's somewhere a little bit outside of the center of the sun.
Is the center of the coordinates, but I mean, how the XYZ coordinates are aligned in space, I don't quite know.
Yeah, no me either right now.
Somewhere on the ecliptic, I bet the first point of Ariès is involved. Not that I would have any idea where that is in the sky.
Right. So what this next example shows is that, so now I'm just considering, I mean, Michael said I was lacking, and he was correct in examples of how would you specify one of these functions. So it allows for an arbitrary force function and arbitrary potential function. So this is assuming the sun is fixed and doing the same thing, where I just have two bodies, the Earth and the moon, with an external force or potential.
Basically a confining potential.
Yeah.
Okay. Pairwise potential is gravity and sun force. Okay. M equals solar mass. Let's force the first body times. Okay, I get it.
Mm-hmm. Or equivalently, you can give that and it comes out the same, which, or equivalently, you can give it as a potential. So that sun potential is given as a potential, the gravitational potential for the sun.
Which means the sun is heavy.
You mean it's a potential as in? So what's your point? That why are you saying that?
So I'm only considering two bodies.
Oh, I see.
Okay, and the sun is considered
no action from moon to sun now.
I see. A fixed potential. So this might be an external potential, like an external magnetic field or something.
Right. Exactly. So it's a demonstration of the external potential, with me not having to spend too much time figuring out physics stuff.
Okay.
And that so that's basically what we have.
It looks excellent, really excellent.
And this is just experimenting. I was trying to play around with scalings and stuff to see if that helped, and it did. This is the older stuff, which I haven't adapted to the new potentials.
Okay, you mean to the new setup of the way MBody?
Right, to the new setup, exactly.
Okay, this looks really good. Let's document it.
Well, so I think to make this successful, Stephen, I mean, I'm happy to continue to be involved and continue to do ND solve stuff, but to really make it successful, we need somebody, I mean, possibly just an intern who's more of a physicist than I am to fill out some of these functions and potentials and test them and see if they work.
Well, wait a minute. Is that what we need to do, or do we need these fast multipole things and all that kind of stuff?
Well, I think first we need to put in a bunch of potentials, and then, seeing where that takes us, we may well need the fast multipole stuff. And the fast multipole stuff is definitely something I'm interested in if it proves that we need it. And, I think I have the understanding of the code that would necessary to do that. So that would be something that makes sense for me to do.
Right. I don't understand why these potentials. Well, we can try and find a physicist to help with putting in these potentials. But I mean, how many potentials do we care about?
A dozen.
Really? So what are they?
I had sent you a list a while ago, I remember. Yeah.
Yeah, I think if you look in the .m file, you'll probably see the old stuff, which still has the list of those things.
The potentials, we might call them.
Yes. I think I kept that.
Were they not very in top? That was a bit fast. I couldn't see it.
Oh, wait a minute. There was something about harmonic there. Let's do a search.
Yeah, these are so only inverse and gravity I did in a new style. I tried to put the harmonic actually in this new style as well.
So I don't understand what's involved, and why isn't it just if you can put in an arbitrary potential, why can't you not just put these potentials in just with their functional forms?
Because I don't know what the functional form is. I don't know where charge comes in, where mass comes in. All of
charge is more interesting because, like, all of them are basically they don't depend on the parameter of the body. One more time, where the charge is more interesting, they depend one more time on the body.
But by the way, Coulomb, why are you saying soft Coulomb? Why isn't there just a Coulomb potential here?
Because that's what Michael gave me.
I'm not sure what you mean by that.
I'm not.
Coulomb is the same as inverse square.
But it has a charge. So I mean, it's a cosmetic difference, right?
Between what?
I'm suggesting that we have one that is called Coulomb, and that Coulomb, instead of having a mass, has a. Oh, I see. It has a mass.
It's a mass. We have mechanical objects moving around.
Right. So it should have a mass and a charge for everybody, and it's still point particles.
Yeah.
Right.
So I think there should be a Coulomb thing there, shouldn't there? Independent of soft Coulomb.
Yeah, of course.
Okay, I just don't see it here. Yeah. Okay, but let's so that one is perfectly real. Harmonic is absolutely should be there. And harmonic, how is that going to work with spring constants and things?
Right. So I think that's a general question. How should we add parameters?
In my opinion, because all kind of that we physically care are really between everybody, I would just also make this for everybody.
Mm-hmm. So what do you mean by that? So wait a minute. You've also got hard sphere, right? Hard. Where did you have that?
That hardcore thing.
Okay. I mean, let's rank them a little bit. Coulomb is clearly important. Hardcore. So hardcore has a parameter.
The radius.
Which is the parameter is radius.
Mm-hmm.
Don't we have to say hard sphere or hard disk or something? Because it matters that it's, not things shaped like, triangles or something like that.
nothing wrong with hard sphere. The typical name is hard core, yeah.
Is it?
I think so.
Okay, let's look it up. But so long as, okay, so it's got a parameter of radius. So in the harmonic case, it's got a quotes parameter, which is the sparse array of spring constants. Am I right?
It depends a little bit like what you see as a physical realization of it. If you literal mean it with springs like Fermi, Poster, Coulomb, then obviously yes.
What else might I think? I mean, other than with quarks or something, I don't know what has, everybody interacting harmonically.
For instance, quarks, yes.
Okay, but it's not a very useful model. So if we're going to do that,
it's extremely useful model for modeling exchange correlation stuff because you can solve it.
Fair enough. Okay. Do we care about linear potential? I mean, in quantum mechanics, we probably would. Right, that's the thing that gives Airy functions with Schrödinger's equation. And it's a reasonable model. Back in the day, at least, it was a reasonable model of the quarkonium energy levels. That's what Rob needed to hear was about quarkonium. I bet you've heard it. I bet you did hear the word quarkonium at some point in your life.
I probably have too.
Okay, so those all seem real. I don't know what is soft Coulomb?
To get rid of the singularity.
So is there a soft gravity as well? There probably should be a soft inverse square.
That would be the natural generalization. Of course, then you could also basically make the softness a body-dependent parameter.
Ugh.
It's the natural coordination of it.
No, I understand. But by the time you're doing that, you might as well just specify. So what happens in this setup if you want to specify the potential between every pair? Do we have a way to do that? Yes, we have a way to do that because you're basically feeding in. What is the potential function? So we say NBody. What are we calling it now? NBody simulation?
Yes.
Okay. So the first argument, what is the structure of the first argument when it's basically doing everything by hand?
If you can either just give it a string like gravitation, or you can give it an association, which is
okay, which had the pair potential function, right?
Right.
Okay, so we probably should be supporting, pair potential. Okay, so now the question is, in the case of pair potential, what does that take? What that takes is so the function f there, and I don't know whether it needs to be in an association, but let's put it in one for now.
Mm-hmm.
So that f takes as an argument, if I'm not mistaken, body 1 and body 2 information, right? The associations for body 1 and body 2. If I'm not mistaken.
That's right.
Okay. I wonder if it needs to know the names. Well, I see. You can always put tags in those body 1 and body 2 things. So a typical form for that would be, this is not that uncivilized. A typical form for this would be hash position. Well, what is this? This would be, wait a second. So what would this look like? I'm just trying to understand what it is.
It could be hash 1 of,
quotes position.
Right, exactly.
Okay. Alternatively, it could be, yes, okay. hash 1 quotes position minus hash 2 quotes position.
Mm-hmm. Mm-hmm. And if you look at like the inverse square one, that's a good example of
okay.
And that works. I think that,
pretty nice.
That seems to work absolutely nicely. So maybe here's an idea for the sparse array thing, Stephen. That's quite general. Is you could have say pairwise interaction or something. That just maybe it's not the right name, but you could give a sparse array to indicate which pairs which pairs interact with which other.
Look, the only issue here is that you don't know the name of the thing you're dealing with. Okay, you've got #1 of mass.
Yep.
You've been already fed the body specifications, but they don't include the names.
Mm-hmm.
If they included the names, right? If what you got was a thing where it also had name, arrow blah, position arrow blah.
Well, it will get that
if it has a name, if you've given it a name. But so then in that case, all you do is the potential is just given by, I mean, obviously it's somewhat inefficient to go looking up all the zero potential, all the zeros here, but there's certainly nothing wrong with, matrix mat of #1 name, comma, #2 name, that looks up the coupling constant effectively in that matrix.
Well, that would have to be, instead of name, that would have to be something like index or something if you're actually talking about a real matrix. You can make a lookup table.
Fine. Well, I mean, actually, yeah, right. So it could feed in. It could be that appended to that association as an index. And if you wanted to, you could look that up. Does that make any sense? Or is this kind of a stupid idea? I mean, the alternative would be, yeah, look, an alternative approach would be this.
Can we not give pair potentials and then give a list of all relevant ones? Those are the ones which we include?
Yes, that would be perfectly reasonable as well. Yeah, that would be reasonable. Pair potential list. And then what would it look like? It would be an association where the left-hand side is the pair and the right-hand side is the potential.
Yeah.
Whatever it is. But then, okay, but then that potential, I see. But how does that work? Is that a function? Yes, it has to be a function which depends on, again, #1 and #2, which are, right?
Right.
Yep.
Yeah, that's perfectly reasonable. That's a single pair potential function, and this is a pair potential list. I like that. Okay.
The only trouble comes if you give both.
Then we have to decide which wins.
Yeah.
I say the pair potential list wins.
I think so too.
Well, actually, you know what? You can have both of them. The pair potential list wins, but for any given pair, if it's not in the pair potential list, it defaults to the pair potential. So, for example,
it would be, no, maybe.
Yeah.
Why wouldn't you? I mean, presumably these, just like sparse array, these things could be patterns.
Okay.
But, well, I mean, basically they'll have to be processed. Presumably what you mean there, instead of 4 or 5 would be a, a body name, right?
Yes. Right. So you'd have to do a match, which we can do in an association.
Yeah.
Yeah. Okay.
I mean, the relevant case would be a linear chain and lattices where you interact with neighbors.
Okay. Yeah, that's a good example.
Mm-hmm.
So an interesting question here is whether we can have a named potential, which is a lattice potential. Right? Does that make any sense? Could we call it lattice? Actually, we could.
I'm not sure what you mean by this.
Harmonic lattice, for example. Well, harmonic chain, it's fairly obvious what that means. If there's an ordering to the elements, harmonic chain just means everybody gets harmonic, potential harmonic force with respect to their neighbors.
But then we must need a method to specify how big the neighborhood is.
Well, it can default to 1, but I mean, that would give us a lot of standard. That should. I mean, okay.
That would give us FPU.
Yes, right. I mean, if it was nonlinear, at least. Okay, so here's an interesting question. Connection to molecule. Because one thing we would like to be able to do is to take a specification of a molecule and say, okay, great, let's run this NBody thing with respect to that molecule.
Actually, we discussed something just this morning with Jason. We, at least for now, we don't have a decent force field for a random molecule.
Well, those force fields are hard to get.
Exactly.
Right. I mean, people have atomic potentials. I don't think they have. I mean, for your isolated xenon atom or something, as I understand it, right? When people do Bose-Einstein condensate calculations and things, don't they have potentials for individual like xenon atoms and things?
Yes. Yes.
And are those calculations semi-classical, classical, quantum mechanical?
I think mostly quantum mechanical.
Okay.
It's just temperatures.
Okay. So which of these potentials, like your Yokawa potential, where is that going to show up, not quantum mechanically, so to speak? And by the way, let me ask this question. In a world of the future, could we imagine doing this with Schrodinger equations?
No, absolutely hopeless, because the dimensionality of the Schrodinger equation scales with the number of particles, and absolutely hopeless even solving a Schrodinger equation in 12 independent variables.
I understand. But in the case, if we were trying to do the helium atom, for example, right?
This is, I think, out of reach.
Okay. But
that's why people do this still classic variational stuff.
I understand. Those are just getting ground states, right? You're saying even getting the dynamics. Okay, so for how many particles can you successfully do dynamics with Schrodinger equations? 3, 4?
1, 2?
What do you mean 1? In a potential, for example. I mean, that's been easy for a long time. 1 in a potential has been pretty easy for a long time.
But but this is why many-body techniques have been invented, so that we don't have the explosion in variables.
No, I understand, because we've got functions instead of other things that we have to compute the wave functions and so on.
Yeah.
But just so I understand, okay, so the one particle Schrodinger equation in a potential, well understood. I mean, I certainly solved those things in the 1970s, right? Okay, 2 particles.
In simple cases, numerically doable.
Okay. 3.
Basically, slowly end of story.
Okay. In the 2 particle case, just out of physics interest, what is does the exact solvability of the classical 2-body problem have a consequence in the quantum mechanical case or not?
Good question. I don't think so. I can't say for sure, but I don't think so.
Interesting. So, okay. So your basic point is, I mean, by the way, I mean, we could imagine packaging, and maybe that's actually Rob probably knows. I mean, in the whole thing that I've been pushing for like 15 years now of, PDE special functions. Do we have those now finally coming for some of the common equations?
What we're doing is we're working on something. Oliver has an intern who's working now to put together, basically taking named equations and putting together, putting together, more examples of different things you can do with that equation. So not so much the.
But are we going to let you feed a named equation into NDSolve?
I think with what he's doing, we may be able to do that at some point in the future. But the problem is there's so many, just like he's doing the wave equation now. Okay, there's so many different scenarios you use that in.
I understand, but the equation itself is always the same.
Yes.
Like you don't actually have to type in the del squared, phi equals.
Right, and I think that's something. But then, how are we gonna, where are we gonna specify the parameters? I mean, it's got the C. I mean, do you include the density?
Arguably, what we should do is we should have a function called, we should just have something called wave equation kernel, and you feed it in phi xt. TX. Is that crazy? Doesn't seem crazy to me.
Kernel has a technical meaning in the stuff that you don't.
I understand, which is not what we want. Okay, wave equation function. And that returns, the idea would be, that would simply return, phi tt, basically phi tt equals phi xx.
Mm-hmm.
Oh, except, of course, for the wave equation, we also need a speed, right?
That was Rob's point. We need, any of them has a lot of parameters.
There's lots of parameters. I mean, do you have a constant density? Do you have a changing density? Do you?
Okay, so here's a suggestion. Okay, so let's imagine that we have a thing, just like, let's imagine that we have a cone, right? We hopefully. Why does it come out? Why doesn't it produce a typeset form here? Do you know?
I don't know.
Okay, so but what does that? It's really weird. But I mean, what I'm asking is, how do I give the parameters to that cone?
Okay, there is an outer layer which is the parameters. Well, make a property association, and you see it easiest.
For that cone.
Yeah, for that cone. I meant string argument.
What the heck? Is that, do I want mathematical solid? What do I want?
I think surface was fine, I thought. But it says retrieval failure. It didn't say it doesn't know.
Well, this is 11.4, so who knows? Who knows? Let's just try this in a more civilized version. Okay, but what am I going to see? I'm going to see some pure functions.
You see double pure function in some of them. An outer one for parameters of the code and an inner one for XYZ.
Okay, so what you're basically telling me is that the right approach here would be for Rob and Oliver and friends to basically curate the equations and put them into a form like these. Okay, this is much more civilized. Rob, are you seeing what I'm saying?
I think so.
So rather than just having them be examples, have them be computable things because they are, so that was just a bug from 11.4. Boy, what is in there? What on earth is in there?
It worked faster for me, but it gives nice results.
57 of them, apparently.
Interestingly, it said for me 49.
Very many.
Yeah, by the way, oh yes, that reminds me. I have to, Sushma, are you involved in the crazy loading?
Yes.
The loading thing and the fact that the blue has changed and shouldn't. And
it shouldn't?
It should be the same blue that we just saw here, the very light blue.
Okay.
Can you try to push that today? Yeah. And if there's a problem, let me know.
Okay.
Like look for defining inequalities. That shows it beautifully. You see, there's the A and the H for the radius and the height, and then the inner one are the...
Wait. Well, this one here, okay, implicit region.
No, that one is not so good. One line down is archetypical.
That is nice. That is nice.
Right. So you can put in what variables you want and
So that would be a good way to represent equations.
I am not 100% convinced because, like for this one, it is nice in one sense, but what I don't like so much is that we fix the order. And for some of the equations, like some of the elastomechanics, which have literally hundreds of parameters,
you got to have an association. It's hopeless.
Exactly.
We can't just have,
that's
have
my
an association.
Point. Exactly.
But there's nothing wrong with that. I mean, the variables, the independent variables, as opposed to the parameters, are fairly small in number, given that we only live in a three-dimensional space and stuff like this.
Yeah.
Mm-hmm.
But the parameters should surely be fed in through an association, and I agree, could be long and messy. I think this is the right kind of way to do it. And I mean, for goodness sake, don't just have non-computable examples, Rob.
Right, I see what you're saying.
It should be in a form like this.
I can talk to Oliver that we get it in such a form.
Yeah, talk with Oliver.
Talking of such things, Michael.
Yep.
And then we should wrap this meeting. Are we ever going to get the coordinate systems stuff?
We are really, really not far away. I mean, we had in the summer this intern. He was really, really, really good, but he didn't get his extension to be allowed to work. So we were trying to fixing it up.
Okay.
It's actually pretty nice.
But so, and is there a top-level design for how all this stuff will work?
No, this is all entities. This was in the entity framework. That's basically a pretty faithful transcription from Moon Spencer, the classic book on coordinate systems.
Okay, I remember
of all their properties. With the one caveat, many or virtually all of them are left-handed, and we are right-handed. So there's a certain kind of tension.
What? Wait. Let me understand that statement. First statement is, what do you mean we're right-handed?
The determinant of certain things give +1 versus -1.
But the determinant of the unit vectors x, y, z gives what for us? That's the right-handed coordinate system.
Yes, that gives for us +1.
And in that book, they used -1 for that?
For many of the curvilinear ones, the determinant is -1.
Okay, well, fine. So that obviously should be fixed, presumably. I mean, unless they had a reason.
That's not so obvious. We are still discussing this issue. I mean, there's something to having a faithful representation of the classic book.
Well, yes, but also maybe we just call it left-handed, ellipsoidal, whatever
That's exactly what we're just working on.
Okay. But defaulting to, I see. So you're proposing. So one question is what to default to. What's an example of one?
To the book.
Okay. What's an example of one where they had it left-handed?
Already spherical.
What?
Yeah. It depends on which order you.
I'm sorry. What is it? Oh, spherical coordinates. They have that way. Well, which way is it for the Earth?
But it depends on you. In which order do you do R, phi, and theta?
Lat long. I mean, that's what we've done for geoposition, right? Is lat long.
Yes, but then we have lat long and then potentially height. So we have height at the end, which probably is also a -1.
Mm-hmm.
Oh gosh. Okay.
It's more a theoretical problem than a practical one.
Why do you say that?
Because how often do you run into this problem that the orientation of your coordinate system really is a big problem? By the end, you calculate a value, make a picture, and it really doesn't matter much in which order your coordinates came.
Fair enough. Okay, interesting. Okay, another twist that not expected. All right. Well, look, in terms of the NBody stuff, this looks really good, Rob. I mean, let's try and get it into at least even in the form you have it, it's already useful. So let's try to get some version of it documented. I think the design is fairly good. I take the point about getting more potentials, but it would already be useful just with gravitational stuff in it.
Yeah, fine. I mean, one final question is, how do you want to, so if we have these named potentials, and some of those can be added, I mean, how do you want to specify parameters for those?
I think with a rule.
Yeah, I would also think a rule. And
okay, so a list. Names. So you put in a list with a rule with name parameters.
So what I would say is something like harmonic, arrow, spring constant, arrow 3, that kind of thing. Do you agree, Michael?
Yeah, I think that seems pretty sensible.
Okay, fine. I can.
The one thing, kind of like some potentials, some forces are not generated from potential, so we should be able to give the forces straight, especially if we have.
I thought we agreed on that.
Okay, yeah, just making sure, because I don't think we discussed such example today.
No, we didn't. But I mean, pair forces.
Just making sure.
Right, something like that.
Yeah, I called them pairwise, but
well, no, that's good. Pairwise.
Yeah, I call it pairwise potential and pairwise force.
Michael, any comments on that? Seems okay to me.
That seems to be a fine detail of the English.
Right. Now I had particle potential and maybe external potential. I think you said would be a better name, Michael.
I think external potential is a better name.
Yeah, external is clearer.
Yeah, I'll change to external then. Fine. So I'll make some of the processing changes, particularly to handle this list thing.
For the external, one thing that would be nice, and I'm not sure how easy this will be. Maybe you use the same trick that you used for the hardcore to confine everything in the box.
Well, what you mean to specify an external potential that is
infinite outside of this and 0 inside, which isn't a good potential for numerics, obviously.
But what's your point? How would you specify that that's what should happen?
Partially, yes.
Well, no. How would you specify that that's what should happen? That it should be in a box?
Now, it would be something like external potential goes to if norm of position greater than 1 infinity, but I'm not sure if that will probably not work out of the box in a dissolve.
No, but I can.
I'm very confused about which box we're talking about.
I mean, I can do like a logarithmic barrier or something, Michael. That's easy enough to do.
You know what I mean? Like, you're totally free until you reach the end of your room, and then you get hard reflected.
Yes,
right. But yeah, that's not going to work. But I can do something that goes. That
you do the same what you did with your Earth.
I mean, in optimization, people typically use these logarithmic barriers, which is really a pretty good smooth mimicking for that.
Well, okay. So one thing one could imagine is it's Coulomb potential, but it's in a box.
I mean, the other one that might be much harder to implement for you would be Venn event.
Yeah. I mean, is that plausible or is that way too difficult for these equations?
Yeah, that could potentially be, but what's the, what's the event that occurs when that happens?
You keep the position and you reverse the normal component of the speed.
Oh, so you do a reflection.
Restitution equal to 1.
Oh, that's easy. That's pretty easy to do in a win event. Yeah, I could certainly do that. Give me something a little bit. Michael, you send me via email.
Yeah. Okay.
Again, I flounder with this physics stuff as it is not concrete because I spend 30 minutes for something that takes you 2 minutes to think about.
I think
it's just because
actually the generalization of this would be a box. Everything inside a region, which is a box, which is the shape of a particular region, and then there's coefficients of restitution and so on.
That might be too much. But I like the idea of
that's getting very, because again, our region stuff really only works in 2 and 3D, that would be easy to do.
Well, that's the case we're mostly interested in.
I suppose that's the case we're mostly interested in.
That is, for better or worse,
specifying a region might be a nice, elegant way.
That would be a fine way. As long as a region can be discretized numerically, then actually the implementation of that is within reason. So send me something a little more concrete on that, Michael. And
I think actually you're even better off if you have an implicit region, because you can quickly test if you're inside, and you can quickly reflect.
Okay, what would it look like syntactically to put a region inside here? I mean, one thing we could do, a little bit weird, maybe.
Well, that would be in the association of force and potential laws, right?
I see what you're saying. So I see what you're saying. So we'd say pairwise, potential, arrow, inverse square, region, arrow, some random region. Oh, nice. Very, very nice.
It will be nicer to specify than if this, otherwise infinity. That's kind of too ideal.
That's horrifying. Yeah, this is what people actually want anyway.
Right.
This is beautiful. That would be magnificent. Okay. So by the way, you're telling me, okay, so this is region, and by the way, we might support something like unit. Well, the unit box is probably already supported as a simple region. I don't know how you get the unit box, but it's probably pretty easy. So by the way, you're saying that connection to molecule is hopeless, basically.
At least for now. We did discuss it, but it's not for the next year.
Okay. This is wonderful. All right. Anything else we need to go over here? Oh, okay. I will send you this.
Just send me that, and we can have discussions about concrete things, the filling and stuff. But yeah, okay.
Fine. Terrific. All right. Thanks.
Good.
Okay.
All right.
Bye.
Yep. Bye-bye.
Bye.